You know, we've all seen them in the movies, right? These shimmering portals that just zip starships across the entire galaxy in the blink of an eye. But are they just a cool sci-fi gadget, or could they actually be real? Well, let's dive in, because the truth behind these cosmic shortcuts is, believe it or not, way stranger and a whole lot more beautiful than anything you've seen in fiction.
I mean, this is the big one, isn't it? It's the ultimate dream of anyone who's ever looked up at the night sky. Could we really just fold the fabric of space-time and step from our little neighborhood out to another star system? Bypass the thousands, even millions of years of travel it would take? The answer, well, it's complicated.
So to even begin to unpack that complicated answer, we got to start with the idea that has completely captured our imaginations for decades. You know, the sci-fi dream of a cosmic shortcut.
Okay, so scientifically, a wormhole has a proper name, an Einstein-Rosen bridge. The easiest way to think about it is like this. Imagine space-time is a giant sheet of paper. Now, to get from one dot to another, you'd usually have to crawl all the way across the surface. But what if you could just fold the paper over and punch a hole straight through both layers? That hole, that's your wormhole. It's a tunnel connecting two places that are ridiculously far apart. Or maybe even two different points in time.
Now this is where things get really interesting. On one hand, the actual math that governs our universe, Einstein's theory of general relativity, it totally allows for wormholes. The equations are there. They work. But then you have the other hand. When we point our most powerful telescopes out into the cosmos, we see nothing. Absolutely zero evidence. Not a single one has ever been spotted.
So what's the deal? Why the huge disconnect? If the math says they can exist, where are they? Well, it turns out the kind of wormhole Einstein's original math describes, it comes with a pretty terrifying and very fatal flaw. And here's the problem laid out perfectly. The very instant anything, and I mean anything, even a single photon of light, tries to pass through a natural wormhole, its own energy causes the tunnel, or the throat, to just catastrophically collapse. It pinches itself shut faster than the speed of light, crushing whatever was inside into a singularity. So it's not a tunnel at all. It's a one-way trap with no exit.
Okay, so is it game over? Not quite. To build a stable wormhole, we'd need something that sounds like it's straight out of science fiction. Exotic matter. This stuff is hypothetical, but it would have a wild property called negative energy density. So while normal matter and energy pull space-time together, that's gravity, this stuff would actually push space-time apart. It would act like a kind of anti-gravity, propping the wormhole open.
And just to give you an idea of the sheer scale we're talking about here, to prop open a wormhole that's just wide enough for a spaceship, you would need a colossal amount of this anti-gravity stuff. We're talking about the equivalent mass of the planet Jupiter, but negative. Now, believe it or not, we have created tiny, tiny amounts of negative energy in labs, but generating it on a planetary scale, that's a challenge that, with our current understanding of physics, is basically impossible.
But you know what? Let's just imagine for a second. Let's say we solved that little energy problem. What would we actually see if we flew up to a stable wormhole? Because this is where we leave the movies completely behind and enter a reality that is just so much cooler.
Right, so in almost every movie, a wormhole is a flat, two-dimensional circle floating in space, like a portal. But space is three-dimensional, so a hole in 3D space wouldn't be a circle, it would be a sphere. You wouldn't be flying towards a flat ring, you'd be approaching what looks like a giant, floating, maybe even shimmering bubble out there in the void.
And as you got closer, you wouldn't see a black, empty void like you would with a black hole. No, forget that whole idea of a dark tunnel. What you'd actually see would be something way more spectacular.
You'd see a sphere that acts like a cosmic crystal ball. Seriously, its entire surface would show you a distorted, kind of fisheye lens view of your destination. The light from that distant star system on the other side would travel through the wormhole's throat and then shine out in all directions, creating the shimmering, spherical window into a whole other part of the universe.
And the experience of actually passing through it would be just surreal. As you cross the threshold of that sphere, the stars of your home sky would seem to stretch and warp, completely wrapping around you for an instant, before just vanishing, replaced by the brand new sky of your destination. Mind-bending, right?
Now, this incredible visual might actually hint at something much, much deeper about the universe. Some physicists think wormholes aren't just for travel, but that they're a fundamental part of reality's fabric. There's this wild theory called ER equals EPR, and it proposes a direct link between wormholes, that's the Einstein-Rosen Bridge, or ER, and one of quantum mechanics' absolute weirdest phenomena,
quantum entanglement, the EPR part.
Quantum entanglement. That's that spooky action at a distance Einstein talked about. It's where two particles become linked, so if you measure one, you instantly know the state of its partner, even if they're on opposite sides of the galaxy. So what the ER equals EPR theory suggests is how they're linked, by a tiny microscopic wormhole. If that's true, it means our entire universe is stitched together by an invisible web of these subatomic tunnels.
And if you thought that was wild, get this. If you can build a stable wormhole, you can probably build a time machine. It's actually a pretty straightforward recipe. You take one end, one mouth of your wormhole, and fly it on a round trip at nearly the speed of light. Because of Einstein's time dilation, time will pass slower for that moving end. When you bring it back, it will literally be younger than the end that stayed put. So if you step through one way, you travel through space. But step through the other way, you travel into the past.
Okay, so with all these mind-blowing possibilities on the table, from zipping across the galaxy to quantum mechanics, it all comes back to the big question: how do we actually find one? And that brings us to the real-world, boots-on-the-ground hunt for these cosmic clues.
Scientists are basically throwing every tool they have at this. They're looking for the weird way a wormhole's gravity would bend starlight, which would be different from a black hole. They're running these amazing holographic simulations on quantum computers to see how information might pass through one. And of course, they're using our biggest and best eyes and ears on the cosmos, like the James Webb Telescope and the Event Horizon Telescope, to scan for any strange shadows or ripples in spacetime that just don't fit the profile of anything else we know.
And this table is basically the spotter's guide for any would-be wormhole hunter. See, a black hole crushes everything at its center and has no exit. A traversable wormhole, though, would have a clear path right through the middle and would lead somewhere else. But the big tell would be visual. Instead of the dark black shadow of a black hole, astronomers would be looking for that one-of-a-kind spherical mirror reflecting a patch of a distant sky where there should just be empty darkness.
And this really brings us to the final, lingering question. You see, the search for wormholes isn't just about finding a faster way to get to Alpha Centauri. It's about probing the deepest connections between space, time, quantum mechanics, and information itself. So, are they just tunnels through the cosmos? Or could finding one rewrite everything we think we know about the very nature of reality?